Hey folks, welcome back to EarthSky. I am Dave Adalian, and today we're going to go check out a really cool exoplanet. And to help do that is the guy who has been studying it quite intensely. His name is Edward Bryant. He's an astrophysicist and apparently planet hunter at the University of Warwick in Coventry in the United Kingdom. He and his team have discovered an unusual giant planet. But it's not unusual because of its size. It's unusual because of the size of its star. It's only 20% the mass of our own star. And this could tell us a bit about how stars and planets like that come to be. Ed, welcome to the show. Glad to have you. How are you today?
I'm very well. It's a pleasure to be here.
Thank you. We're really glad you could come and share this exciting news about TOI 6894b. Rolls right off the tongue. What exactly has your team found? What's it? What do we know about it? Let's take a look at a picture of it. We got a picture here.
Yeah. So what we know about this planet, TOI 6894b, is that it's roughly the same size as Saturn. So it's pretty much the same diameter as Saturn, and only about half its mass. And so you might think it's just a standard similar to Saturn in the solar system. But what makes this planet really exciting is the mass of its host star. Its host star, the star it orbits, is just 20% the mass of the sun. And so this is a really small star to have been able to form such a planet, really. And that's what makes this so exciting, is that we don't really have a good understanding of how this planet was able to form around such a small star.
So it doesn't really fit the model that we've come to expect for these kind of objects, right? Is that what we're doing here?
Yeah, absolutely. Yeah, absolutely. I mean, so when we think about these giant planets, one of the main leading theories for how they form is this process called core accretion, where surrounding the very young star, you have a protoplanetary disk. So this is a huge disk of gas and rock and dust. And what we think is the solid material, so the rock and the dust, collides together and combines to build up a giant, massive planetary core. And then once that core is massive enough, it can accrete a lot of gas from the disk and form a giant Jupiter or Saturn-like planet. The problem for this system is that we expect that the mass of these disks, so how much building material is available, scales with the mass of the star. So around a star as low mass as TOI 6894, just 20% of the mass of the sun, we wouldn't have expected there to be enough material to be able to form a planet as massive as the one we found.
Okay. Wow. Okay. So how did you make the discovery itself? Where did you get the data to find TOI 6894b? And how did you analyze it in order to discover the planet? Yeah, that's a mouthful, isn't it?
Yeah. So sadly, with these planets, so just one the name, with the planets, we don't actually get to give them sort of attractive names ourselves. They get given classifiers more than names based on how the planet was discovered more than anything else. So right. The planet, I initially discovered it using data from the TESS mission. So TESS is a NASA satellite in space. And so the T in TOI stands for TESS. And what it is it's a TESS object of interest. So that's where the acronym comes from. And then the 6894 means it's nearly the 7,000th star that TESS has reported a candidate transiting planet around. And then the lowercase b means it's the planet, not the star.
The planet, not. So we can just call it the toy planet.
We can call it the toy planet if that's easier.
In fact, let's take a closer look at the system. We've got a little video that I made using a tool, the Exoplanet Explorer, over at NASA. I suggest you guys go check this out. It's fascinating. Anyway, what are we looking at here, Ed? What do we got?
So what we're looking at here, this is the system. So you have, what you can see is that this giant planet is very close to its host star. It orbits its star once every 3 days. So it's really, really close. And with these very close-in planets, often they will transit their star. So what that means is that when the planet passes in front of its host star as you're viewing it from Earth, it actually blocks out some of the light that's being emitted by the star. And this is how we find these planets. Using satellite missions like TESS, we can monitor how bright the star appears to be, how much light is reaching us. And then every so often, every few days, for a planet like this, we'll see a decrease in the light we receive from the star. So the star will look slightly fainter. And by looking at these repeated transit events, that tells us that could be a planet transiting this star. And obviously from the spacing between those transits, we know the orbital period of the planet, so how far it is from its star, and from how deep the transits are, they can tell us the diameter of the planet.
Okay. And here we have this is the tiny little star in question, just 2/10 the size of our star. That's amazing. And so how did we end up with a planet so large around a star so tiny? We've got some clues here, obviously, but aren't you going to have to put together a theory for this? I mean, is that what you're working on now?
Yeah. So that's what people are doing a lot of work on now, is trying to understand more of where this planet came from, because it obviously doesn't fit with what we might expect from sort of the classic formation theories. And there's sort of, for me at least, there's sort of two leading ways that this planet may have been able to form. The first off is that it could have formed through an entirely different mechanism, one called gravitational disk instability. So this is
that's enough. Can you explain that to us again?
Absolutely. Yeah. So it's gravitational disk instability. And what this is instead, within your protoplanetary disk, instead of building up the core by colliding the solid material, the disk itself actually becomes sort of unstable and can fragment directly and collapse into planets if it fragments in the right way under the right conditions. And there's still a lot of work being done to try and understand this method and how these disks fragment, and under what conditions they might fragment in such a way as they can form planets. But if you take the assumptions that these disks can fragment, then there's been some simulations that have shown that it could be possible to form giant planets like this around these very low mass stars. So this could be one pathway through which this planet may have formed. But I say there's still a lot of work needs to be done to try and understand the exact environment you need to get that disk to fragment in the right way, and also what planets form from it.
Oh, wow. That is so fascinating to me. I just want to know how we got where we are. Let's go back and take a look at this picture again. And, I was looking at the NASA visualizer, and I realized this is not, it's the same. It is sort of the same color as Saturn. I expected it to, as a methane world, to be sort of Neptune blue or sort of colored like Uranus, but it's not. Why not?
Yeah, so we don't really know exactly what color this planet will be. We sort of make estimations, and we don't actually know whether there is methane in its atmosphere. We think there probably will be. But just currently, all we have is the radius of the star, the radius of the planet, its mass, and its temperature. And we get the temperature from how close to the star it is. And using those, we can predict that we might see methane. We might even see ammonia in the atmosphere as well. And it's sort of these sort of give it that bluey and the white sort of color, or may do. And the way we want to find out more of what's in the atmosphere of the planet, is through observations with JWST. And so there's some observations for this planet with JWST scheduled to take place over the next year. And with using those, we can actually take a look into the atmosphere of this planet and see what's in there, and see whether we find gases like methane, whether we find ammonia, or whether we find something else that we didn't expect. So that just in of itself will be very exciting to take a look at.
So you're going to look at, I suppose, the spectrum to see what chemicals make up the atmosphere. Do you need a light source from behind the planet for that, or does it?
Yes. Yeah. So the light source we use is the host star. So what we do is we measure the light from the star, and the star itself will have a spectrum with different gases in the star. And then what we'll see is we'll continue observing the star as the planet transits and passes in front of its star. And we can actually look at the light coming from the star, passing through the atmosphere of the planet, and then coming all the way to our telescope. And by doing that, we can start looking at what gases and molecules are present in the atmosphere of this planet as they interact with the light as it passes through.
So does Toy Star and its toy planet, does that got all your attention right now, or you have anything else you're working with?
So currently, this planet has been taking up a lot of my attention because, it's very exciting. And as well as looking at just what other molecules are in there, looking at the atmosphere as well will tell us more about the composition of the planet as well, and more of what exactly the planet is made up of. We might be able to use these observations to learn more about how massive its core is, which is then quite important if we're trying to understand how it formed and where it came from. Understanding how massive its core is, what other elements are in its atmosphere are all very important when we're trying to potentially benchmark or test our new theories for how this planet could have formed.
Okay, so you say benchmark. So that means we're setting a standard that we can use in future exploration, right?
Yes, to some extent. So this is a very exciting new discovery is in terms of these transiting giant planets. This is the lowest mass host star that we've ever found one around in terms of these transiting giant planets. And so this really is setting that new extreme in terms of how low mass you can go and form these planets in terms of a planet that we can really study in great detail and learn a lot about. So when we are coming up with these new theories and trying to understand how these low mass stars can form giant planets, this will be a really important data point in terms of matching those theories against.
Wow, that's really, it's so cool to have an insight into the process of how we hunt for all of these now thousands. We found thousands of exoplanets and documented them. Ed, thank you so much for being here. That was a great talk. I hope to have you back when you get some of that James Webb data in and we have further insights into the toy planet, into TOI 6894b and its host star, that tiny little guy. All right, Ed, thank you. And we will see you next time. Okay.
Thank you very much. See you later.
Well, folks, as always, thank you for joining us. EarthSky is here every weekday at the same time, 17:15 Universal Time Coordinate UTC. And we've always got new and fascinating stuff coming up. Hit the subscribe button so you do not miss out. On Friday at our normal time, we are having a June solstice party. We'll be sharing your thoughts and the thoughts of some of our guests and our own thoughts on what the solstice means to us. And we hope you can be there. Hit the like button if the spirit moves. One Earth, one sky, EarthSky.